It's my great pleasure to introduce Carlos Feder and Tomas Feder to give the talk today at Google. And they're going to talk about a practical computer program that diagnoses diseases in actual patients. And before we start, I'm going to tell you a little bit about Carlos and Tomas. So Carlos Feder was born in Vienna, Austria. He graduated from the School of Medicine, University of Buenos Aires, Argentina. In that country, he practiced internal medicine for 30 years and at the same time taught this specialty at the university hospital. For the past half century, his obsession to invent and improve an algorithm for computerizing medical diagnosis led him to review existing relevant literature, publish papers, and secure research grants from numerous pharmaceuticals. In 1983, he immigrated to Palo Alto, California, where he practiced his specialty for another 19 years before retiring in 2002. Since then, he dedicated most of his time organizing his experience and novel ideas and describing his medical diagnostic algorithm that promises to be a breakthrough in the field. He's the author of 2 books, Computerized Medical Diagnosis, a novel solution to an old problem, published in 2006, and a practical computer program that diagnoses diseases in actual patients, published in 2008. And this book is co-authored with Tomas Feder, who is our our second speaker of the day. Tomas Feder is son of Carlos, was born and grew up in Buenos Aires, Argentina. He obtained with honors his bachelor degree from the French school in the mentioned city. In 1983, he immigrated with his parents and sister to the United States, where he received his PhD in computer science from Stanford University. He was one of the outstanding students of his prestigious advisor, Don Knuth. Tomas worked for several years as a researcher at IBM. His curriculum includes over 120 publications, personal and with co-authors around the world. With Masu Vardi as co-author, they published a landmark paper in 1993 conference version and 1998 journal version that created a new specialty of computer science named constraint satisfaction, crossroads of mathematics, logic, and computer science, which became important in the field with congresses held worldwide, to which Tomas is always invited. And without further ado, let's welcome Carlos and Tomas.
Thank you. Can you hear me, everybody? So, good morning. First of all, I want to thank Anzu, Iliad, Boyan, Gagan, Agarwal, and Google for providing us with this opportunity to present our ideas. First of all, I want to call your attention to this title, Essential Need for an Efficient Computer Diagnostic Program. Because why is this need so essential? Well, there is among us an under-recognized killer that kills or disables a great number of victims. And this killer is called diagnostic errors. Diagnostic errors are extremely frequent, much more than you can imagine. Because most doctors are unaware about committing these mistakes, and if they become aware later on, the last thing they want to do is to publish that. So therefore, we don't have a registry for diagnostic errors, and therefore we don't have statistics of how often they occur. The good news is that the majority of these diagnostic errors are inconsequential because Mother Nature takes care of them Most diseases, let's face it, cure spontaneously in spite of the doctor. So, but there is still a minority that can have dismal consequences like long-term or life-term disability or even death. And in a world that has more than 6 billion inhabitants, this minority could represent a very tragic number. This diagnostic uncertainty leads doctors to order an excessive number of futile tests and procedures based on their imperfect memory, limited experience, or feeling of the gut, instead of ordering these tests based on a probabilistic determined benefit. And this is very harmful to patients, and it's also harmful to the socio-economic system because it's a waste of already limited medical resources. Why are these diagnostic errors so frequent? Well, there are different opinions. In my view, there is no human brain able to remember several thousands of known diseases that we have now, and the several thousands of symptoms, signs, lab results, X-ray results, etc., that which these diseases manifest themselves. And by the way, we use the term clinical datum singular or clinical data or data for any, as a generic term for any of these symptom, sign, or result of some kind of procedure or test. Doctors are not even capable to learn all the diseases that exist nowadays. Perhaps in our area, in the Bay Area, these errors occur less, but they still occur very frequently because we have excellent hospitals, we have prestigious universities and medical schools, we have easy access to specialists. But imagine what happens in an underdeveloped area, even of our country, or in developing countries where sometimes not even a regular doctor is available, let alone a specialist. At the time of the diagnosis, if the doctor doesn't remember the disease or has never learned it, this means then that the diagnosis is missed or misdiagnosed. This problem is compounded by the ironically called health maintenance organization, HMOs, managed care, you know. These companies press their doctors to see a patient in a very limited time, perhaps in 15 or 20 minutes, and it is impossible to do a good job in such a limited time. So how can we expand our memory? How can we increase our speed to diagnose? Well, I understand that you are mostly computer scientists here and engineers, so you know more about computers than I do. But computers have changed the way, have changed the world, and they can change the way medicine is practiced too, with their tremendous storage capacity, speed of processing, and portability of knowledge. We are asked, when we give a talk like this, we are frequently asked whether such programs, diagnostic programs, do not already exist. Well, I listed here the ones that are best known so far. And we challenged these programs with actual real patients, with real cases, and the results were quite disappointing. What happened with this program is that they are excellent reminders of unusual diagnoses of rare diseases, but they are unable to pinpoint exactly the disease that is afflicting the patient. Therefore, they are considered more like educational tools for medical students or for young doctors that are not yet very experienced, but not actually diagnostic programs. And the authors of these programs recognize that in the disclaimer that appears at the beginning when they open the program. Therefore, these programs are poorly accepted by practicing medical doctors and seldom used, actually. So let's now remark what are the advantages of our program compared to previous existing programs. If you provide a computer with a clinical data, or that means symptoms, signs, etc., of the patient, they will retrieve a long list of potential diagnoses, perhaps 50, 60, 70 diagnoses, and some programs stop there. So the poor doctor is left on his own to find out which of these 60 or 70 diagnoses will be the actual one that corresponds to the disease of the patient. Our program also, at the start, offers a long list because each clinical datum present in the patient evokes one or more diagnoses. But our program goes further. It rules out the non-viable diagnosis until only one or more than one that really afflicts the patient are left in the list. So clinical data present rule in diagnosis, bring it into the so-called differential diagnosis list. And clinical data absent in the patient rule out diseases. And that is a principle that we use in our program. The other problem of existing program is that they don't have a method to accurately determine the probability of each diagnosis. They use Bayes formula or they use some scoring system, but none of these systems are accurate. So I suppose also that you know better Bayes formula than I do, being a computer scientist. But anyway, it's a conditional probability of a diagnosis given a clinical datum. Bayes, so much used in medicine, however, in diagnostic application has two flaws, two important flaws. The clinical data must be independent, which is not the case in medicine. In medicine, all the symptoms of a single patient are interrelated because they obey a common cause or a common lesion, so they cannot be independent. I give an example. Suppose a patient has a cancer that obstructs the biliary duct that takes the bile from the liver into the intestine. If this duct is clogged, then there is a substance in the bile called bilirubin that gives this yellow color that spills over with the whole bile into the blood. And that produces what is called the jaundice, the yellow discoloration of the patient that has such an obstruction. And then the excess of bilirubin is eliminated through the urine, and the urine takes this dark brownish color like Coca-Cola. And as the bile cannot reach the intestine because of the obstruction, the stools are very light colored like clay. So we have here four symptoms. Increased bilirubin in the blood. We have a dark urine. We have very light stools. And the patient has a jaundice. So Bayes considers these data independent, and they are not. They are all closely related to the point that they are almost like synonyms or like are redundant. So if Bayes gives a value for one of them, then the next one, then the next one, the total probability reaches an improper high value, you know. Same with scoring systems. I give a kind of rate to each symptom and then adds up all that. We have the same problem that we have with Bayes. So we created, actually Thomas, our son, created the minimax procedure to accurately determine the probability of the diagnosis, of each diagnosis. And this minimax procedure, based on clinical data present and what's called the positive predictive value of this clinical datum present, that we cannot explain in detail today because it is a separate talk of 1 hour, maximizes the probability, raises the probability until it reaches a confirmation threshold where this diagnosis is accepted as confirmed and final. And on the other hand, it minimizes at the same time the clinical data, the probability based on clinical data absent and based on what is called the sensitivity of the clinical datum absent. Sensitivity is simply the frequency with which each diagnosis manifests a symptom. For instance, a patient that has bronchitis will have almost always cough. And this cough is very frequent. So cough has a high sensitivity for bronchitis. So if cough is missing from the patient or in the patient, this is a powerful reason to rule out this disease. So this is more or less in very broad terms how the minimax procedure works. The other drawback of Bayes is that the diagnosis must be mutually exclusive. That means that one diagnosis in this long list will be the winner and all the other diagnoses will be the losers. And that is not correct because patients many times are afflicted by more than one disease. I give you another example. A patient can have a myocardial infarction that weakens the heart muscle, so it develops another diagnosis, another disease called congestive heart failure, which is a complication of the infarction. And then the injured muscle starts to beat irregularly, so there is an irregular heartbeat that is called an arrhythmia, and Bayes is not able to discriminate that. Bayes try to explain all the symptoms of the patient with only one diagnosis. Our minimax procedure is perfectly okay in diagnosing what we call concurrent diseases. Cost of obtaining each clinical datum is also a very, very important concept not considered in any of the existing programs that I had a chance to review. Cost in our context means not only the expense in dollars you have to pay or the insurance company has to pay to obtain the clinical datum, but also the risk for the patient and the discomfort. And based on these three elements, we consider 4 cost categories: no cost, small cost, intermediate cost, and great cost. And I'll give you an example of each. No cost are clinical data obtained simply from the history of the patient or from the physical examination that the doctor performs at the office. We call it no cost because it's supposed that it's not charged extra part of the cost of the consultation. Small cost would be a blood test, for instance, how your cholesterol is doing. And this doesn't cost so much. The discomfort is only a prick in the vein. Well, that's okay, right? And the risk is essentially inexistent, unless you go to this crazy woman that you have heard years ago in an important laboratory in Palo Alto, that instead of discarding the syringes, reuse them, washing them with soap water. And that created a mess because hundreds of patients had to be checked for HIV and hepatitis virus to see if they were infected or not. But that is an exception of the rule, right? Intermediate cost would be, for instance, a colonoscopy. It costs more. It's not a pleasure to have introduced in your rear a tube long like this, like 4 feet. And there is a small risk in that because there are cases reported with perforation of the intestine with the instrument, so that's a pretty nasty thing to happen. And finally, great cost would be a test like a laparoscopy to look inside the abdomen with an optic instrument to see the organs inside. And that is, of course, more expensive, needs general anesthesia, and has some complications also. So, but cost is very important for the patient, for the insurance companies, and also for the entire socio-economic system. On the other hand, cost must be counterbalanced by the benefit of the test. And how do we define the benefit of a clinical test? The more it increases the probability of a diagnosis, the better benefit, because it brings it closer or to the level of the confirmation threshold. And also, how much it reduces the probability for those diagnoses that has to be ruled out because they approach them to the deletion threshold where the diagnosis is definitively ruled out. Now, we can establish the benefit of a test virtually before ordering the test, simply by running the minimax procedure and see how much it would increase the probability if the test comes present or positive in the patient, and how much it would reduce it if this symptom is absent. Now, knowing on one hand the cost of the test and knowing on the other hand the benefit it produces, we have the best chance to select the best test next to investigate in the patient. We always order the less cost category test first, before escalating to a higher test if necessary, higher cost test. And inside this cost category, the lowest possible, we choose of course, a clinical datum that will most increase or decrease the probability of the diagnosis. Now, here comes another problem now. The computer looks at all the diagnoses in the differential diagnosis list and looks all the clinical data that have not yet been investigated in the patient. And that is a tremendous long list, as you will see in the demonstration of a case that I will show you. So we had to devise heuristic strategies to reduce this huge amount to a manageable amount of tests to be ordered without compromising the accuracy of the diagnostic program. For that, we devised some parameters that can be set at different values, and this will retrieve then this what we call abridged output files that show this reduced in number list of data. But that you will understand better when we do the demonstration. No? So for now, have a little patience, please. And here's another problem. Many times, as I said before, the patient is afflicted by more than one disease. And what happened with existing programs, perhaps some program will diagnose from these 3 diagnoses I told you, myocardial infarction, congestive heart failure, and irregular heartbeats. Perhaps it will diagnose correctly the congestive heart failure, but will miss the diagnosis of myocardial infarction, which is a cause of all that. And that is very bad because both the complication and the disease must be treated simultaneously. So our program to solve this problem creates, or we created this, what we call complex clinical presentation models, where all the diseases that are connected in some way statistically or by mechanisms, pathophysiological mechanisms, are listed together. It's only a list of diagnoses that used to be connected in some way. And if one of these diagnoses is confirmed by the computer, then automatically all the other diagnoses are transferred into the differential diagnosis list to be processed like any other diagnosis with a minimax procedure to be confirmed or to be ruled out. And then there are another problem. There are interactions between diseases and drugs. I give an example to illustrate that. A patient has a myocardial infarction. The landmark symptom is an intense oppressive chest pain in the middle of the chest. But if the patient is at the same time diabetic, this diabetes can cancel the chest pain. And that is very risky for doctors and for computers, because if an important symptom or a frequent symptom with high sensitivity, like chest pain for myocardial infarction, is missing, then the doctor and the computer tend to rule out the diagnosis of myocardial infarction. So what our program does automatically, if diabetes is confirmed, the symptom, chest pain, is removed from the disease model myocardial infarction. And the computer is forced to recommend a better test, more reliable, like an electrocardiogram, or perhaps the increase of troponins in the blood, which is a marker for acute myocardial infarction. Synonyms is easy to handle with our program, and the program is also easy to update, but as we are getting short of time, we will skip that. It's not so important. And let's summarize what we said now by underscoring the socio-economic advantages of our program. Number one, it is expected to significantly reduce the current numerous diagnostic errors and the dismal consequences of these errors. Second, it will save specialist consultations, which is important in some urgency situations where the specialist is not readily available, or in underdeveloped countries where the specialists don't even exist. It will reduce significantly the number of these futile tests and procedures that harm the patient and the socioeconomic system. On the other hand, if a test is really necessary, proven by this program that it has to be obtained to confirm a diagnosis, then even if it's costly, it will be an argument for insurance companies not to curtail that, not to disauthorize it. Let's keep done. It will protect healthcare providers against unfounded malpractice liabilities, because if this program hopefully someday becomes state-of-the-art for diagnosing, if the doctor follows the correct steps and that is logged in the computer, that would be a powerful proof in court that the doctor proceeded correctly. And it will help also, I'm sure, if it works fine, to overcome the current well-known resistance of physicians to use these programs as an aid for diagnosis. Well, let's do the demonstration now. This is a real case. It's not a fabricated case. It's a real patient. And this is a 32-year-old white female grade school teacher with recent onset of palpitations. 6 months ago, she lost her job, followed by nervousness and depression. At that time, a complete physical examination and basic lab tests were normal. She was treated with an antidepressant without improving. Her medical condition gradually worsened, and recently the mentioned palpitations added to the clinical picture, motivating the present consultation. The medical examination revealed the following clinical data. Excuse me a minute. My mouth is getting dry. So, wait a moment. Our program has, among others, 2 input files, one for clinical data present in the patient and one for clinical data absent. The patient showed these following symptoms. She had palpitations, nervousness, depression, she was fatigued, she was sweating more than normal, she lost weight, and she had diarrhea and some shortness of breath. And the examination showed tachycardia, which means accelerated heart rate. Her skin was more delicate than usual for the age, and also the hair. She had exophthalmos, which is protruding eyes with a larger opening of the eyelids. And the palpation of the neck showed an enlarged thyroid gland here, which is called a goiter. And also she had some auscultatory phenomenon with a stethoscope when you listen to the heart. I don't want to waste more time with that. She also had a muscle weakness, and she had tremors, like me now with this presentation. Okay, so, and please notice that these symptoms are sorted by cost category. These are all no-cost clinical data, and they are sub-classified by the procedure to obtain them. This is the file for clinical data absent. I don't recommend at the beginning, at the first diagnostic round, to put the clinical data absent, because doctors document a lot of clinical data absent, and if you enter all the data, it's cumbersome, and most of the data don't even correspond to the diagnosis already ruled in, you know. So let's start for the next round, when the computer tells us better which test to order next. We put only one symptom here, that is the gender of the patient. By putting male absent, we rule out from the beginning on every disease that afflicts exclusively males, like a prostate cancer. Women have no prostate, so they cannot have a prostate cancer. I apologize, instead of putting female present, the way Thomas wrote the program, it was more practical to put male absent, which means that the patient is a female, right? Okay. We run the program and we obtain, I don't know if you can read that, is it large enough? It doesn't matter. Anyway, there are 20 diagnoses that this clinical data present brought up, you know. And these diagnoses are sorted by decreasing probability. And I apologize again, because instead of putting the probability in decimals or percentage, Thomas decided to put it in per mil without the 0 and the decimal point in front. So you will have to do a little exercise. The first diagnosis has a probability of 818 per mil, so that means 18.8%, right? Okay, 20 diagnoses. Now we open the output file that gives all the clinical. It's a very busy slide, don't worry about that, don't read it. I only want to show you how, this is an incomplete list, how many clinical data were not investigated yet to clarify which of these 20 diagnoses are the actual one, the confirmed one. These are, it says a number here, 242 tests. You cannot order 242 tests in a patient. You will kill the patient and you will kill the socio-economic system, right? So I show you now what happens when we use these parameters. And again, we have no time to explain that. That corresponds to another talk of 1 hour, as I said. But trim parameters are those that eliminate from the beginning on those clinical data that increase only very little, let's say 10% or 20% the probability, or only reduces at 10 or 20%. So we can disregard that from the beginning on. And we can also manipulate the confirmation threshold or the deletion threshold. That will also have an effect on the number recommended. Anyway, if you use these parameters, we set them to what we consider the default values, then the list of 242 clinical data are now reduced to only 85. That still sounds quite a lot, but if you consider that most of these tests are in the no-cost category here, then the doctor, the only thing he has to do is to go back to the examination room where the patient is still waiting in her examination gown, ask for more questions he forgot to ask in the first place, and also to complete his physical examination, paying attention to these physical signs that he omitted to do the first time. No? And then I highlighted in yellow the only symptom that the patient had present, that is a hypersensitivity to heat, and all the gray highlighted clinical data were absent in the patients. So what we do now, we copy the yellow present data and then paste it into the clinical data present list. Here's the only one that we have to add to the previous listed symptoms. And we do the same with the clinical data absent in the clinical data absent file. And here, all these are clinical data absent, and now we paste that, we save it, and we run the program again and see what happens. From the 20 diagnoses we had at the beginning, now only 2 are left. The first one is hyperthyroidism, when the thyroid gland produces too much hormone with all the symptoms that you have seen. And mitral stenosis is a lesion of a valve inside the heart called mitral valve that gets narrowed because of a scar, a disease. So my question is, hyperthyroidism has now a probability of 67%, and mitral stenosis has a probability of 10.3%. Are we satisfied with this result or not? Well, we are not satisfied, because in order to confirm hyperthyroidism, we need a probability of 90%. That is our confirmation threshold. And mitral stenosis is almost ruled out, 10.3%. Okay, we need 10%. But let's do things properly, and let's try to be more specific. So we look again at the average data cost procedure, at this average that before had 85 data recommended. Now this list recommends only 8. Of course, less diagnosis, less data to investigate. And for that, we have now to prescribe some tests to the patient, some lab tests. Here are the ones that we are ordering. And we order also ultrasound of the heart and echocardiogram, which is non-invasive and shows us the valve if it's really narrowed or not. And the result is this. These 2 tests that we add now to the clinical data present show that the thyroid hormone production is really increased. And as data absent, we put here that basically the patient had no mitral stenosis as one of the potential diagnoses. And now we run the program again, and bingo. We have only 1 diagnosis left, hyperthyroidism, with a probability of 100%. And that ends this demonstration. Now, I want to finish up, because we are very close to the end of time. What happened so far with our project, and what are we expecting in the future? In 2006, after many years of research and grants and publishing and teaching, we had together the theory behind our program. In this, we published our first book that was already presented to you. In 2007, Thomas, our son, Thomas Feder, wrote the program that executes all this program. And that provided us a prototype. And that was really a revelation, because it confirmed essentially all of our theories. It dissipated about 20 uncertainties we had, were completely dissipated. we challenged the program with real cases, and it was diagnosed beautifully, you know. So many were the improvements, the simplifications of the algorithm, etc., that we decided to write a second book and publish it, which is the same title as today's talk. And our prototype includes so far 60 diseases in the database, and as I said, diagnoses correctly about 100 real cases we challenged the program with. Now, what next? Our program, or our system, in order to be really useful, must include all thousands of known diseases and all the clinical data that we know currently that are manifested by these diseases. And that a single person cannot do it. We need a team of specialists that provides this, that estimates the sensitivity, only the sensitivity of each symptom for each diagnosis, and the rest is taken care by the computer. So it's not a difficult job, but it's a long job that the team has to do. And they have also to put together these complex clinical presentation models that associate in some way related diagnoses. We hope that Google or somebody else may help and support us with this project. The program of Thomas is very good. It executes all needed functions, but it's not a glamorous program that you click icons or you click a menu and this colorful windows open. That also should be done by a professional programmer because Thomas is not a programmer. Thomas is a computer scientist, theoretical computer scientist. But the program works perfectly well and is pretty user-friendly. What next? And that is our last slide. Our diagnostic system, once implemented with all known diseases and clinical data, is expected to provide invaluable diagnostic benefits to patients, physicians, nurses, health insurance companies, malpractice lawyers, malpractice insurance companies too, and I would say the entire medical establishment. So thank you very much, and we have a few minutes left for questions and answers, right? So, any questions? Sorry, yeah.
Am I supposed to, is there a microphone? No. You'll just repeat this. Okay. So my question is, maybe this part isn't envisioned yet, but it seems like one thing that would benefit the system would be if it updates. You said that it's easy to update. If it updated with any mistakes, let's suppose that a physician confirms a particular symptom in a patient, and it turns out, and the system ends up getting a diagnosis, and then later it turns out that the diagnosis was wrong because perhaps there was user error, the physician misspecified the symptom, or perhaps patterns have changed in the population and that symptom no longer has the probability impact that it used to have. And so it seems like there could be the opportunity for feedback into the system as changes in the population occur that cause the probabilities to change. The system could update itself and start updating the change, the differential diagnoses, basically. Mm-hmm. Is there any idea of doing that, and would there be privacy implications for the patients whose data is ultimately being put into the system?
Okay, so far I understood the question. It has two parts. How do you update the system, number one? And the other question is how reliable the system is. No? Regarding the reliability of the system, so far, with this 100 of cases we challenged the system, it worked very well. The diagnosis was essentially correct every time. No? Of course, we have to see what happens with a larger number of diseases and clinical data and all that. Now, update, I jumped over that because of lack of time, but this is a very, very important and good question, let's see if I can show you another slide here that is quite curious, you know. Existing programs, I would say there are three types of programs. One is based on, like ours, I would identify it with pattern recognition. There are only lists of symptoms that matches symptoms in the disease model and bring it up, etc. Then there are the type of programs that are based on mathematical formulas. And you see the most crazy and sophisticated formulas. One Patrick created a whole book full of formulas from the beginning to the end, and I'm convinced that such programs are completely divorced from clinical reality, from the daily nuances of a diagnosis. No? And then many programs are like trees or like networks, you know, that this cause produces this lesion produces these symptoms. Many of these links are not even known in medicine, and some links jump over a node and go to a more distant node. And these programs take months, or years probably, in implement. And then after 2 or 3 years, they are obsolete because medicine changed. They have to start again from the beginning on. I would like to show you, one program is the Internist program, which was very popular among researchers, and still today they try to fix it in some way. But let me show you this slide because it's a little funny. 1 second, please. And show, I have to go here to the corresponding slide. If I can quickly find it, 1 second, please. Here. Yeah. Can you see that? On the top of the slide, there is this relation. The cause of the disease produces a lesion by pathogenesis, is called the mechanism. The lesions produces clinical data. But this is a simplistic line. Then one cause can produce more than one lesion, and each lesion produces many symptoms, you know. So then the network becomes more entangled or tangled. The same author calls tangled. And look what happens. I want to show you this slide here. This is only a very small portion of medicine, only a very restricted look. Imagine the whole medicine put together like that. It's impossible, you know. It will never work. Our program, you only have, if there is an update, let's say a new test is invented, no? Then the only thing you have to do, you have to add it to the disease model with a corresponding sensitivity, how frequently this test is positive in this disease, right? And if necessary, you can add this, it's a new diagnosis, you add the new disease. You add the new disease with all its symptoms and the sensitivities. And perhaps you should still add this disease if it's connected to other diseases in the complex clinical presentation model. But that's all what you have to do. The computer takes care of everything else, you know. I don't know if that answers your question.
Yeah, that's exactly.
Good. Yeah.
So I'm struck by the fact that this relies on the sensitivity.
On what, sorry?
It relies on, your model relies on the sensitivity as the key to everything that it's doing. And yet it relies on individuals to say how accurate it is in total, right? As for a particular test is associated with a disease. Yet what you'd really like is to kind of use the wisdom of crowds, what many hospitals, many people have found for that particular test, because one individual may have limited experience, or, you know, the more obscure your disease, the more difficult it is to know. So I was wondering if you could say something about that.
The question is, and you correct me if it's not so, how to establish a reliable sensitivity of a clinical datum for a specific disease. Sensitivity also always depends on the datum and the diagnosis, of course, both poles. Well, there are three methods to determine the sensitivity of each clinical datum for each disease. I call it first the retrospective model. You take, like in this book, that is an old book, but I used it a lot, that tells you the sensitivity of each clinical data for 50 diseases, 50 diagnoses. You, like these guys did, they say they took 1,000 charts for each of these 50 diagnoses and did a statistical tabulation to see how often this data happen in the corresponding disease. That is one method, retrospective one. The other method would be the prospective method, to say from now on we will tabulate each patient, and if he has bronchitis, we will look in 100 patients or 200 prospective patients how often cough shows up, right? That would be a better method, because the doctors who do that should be trained specially not to miss to document the clinical data, because if it's not documented in the chart, it's as the patient didn't have the symptom, you know? And that is would be an ongoing process. Only in 2 or 3 years we'll have a good statistic, right, in this sense. Now there's a kind of rebirth of universal electronic storage of medical charts that will help a lot, you know. The government is very interested in that. Google come out, I believe, with Google Health, where patients can storage their clinical history at Google, and any doctor who needs that can retrieve it. And Microsoft came out with Health Vault, same program. So if that materializes, that will help the prospective method. And third, it can be estimated by doctors. Doctors know how often, more or less, a patient with bronchitis has cough, how many times a patient with myocardial infarction has chest pain, you know. I didn't trust very much these methods, because if you ask two doctors, there will be a big difference, sometimes of 20% or so. However, our program showed that the accuracy of the sensitivity is not so critical. It accepts pretty large discrepancies. And also, what was I going to say? Something else I want to say about that. The discrepancy is more with the symptoms taken from the history of the patient, as you mentioned, and more at the physical examination. But as soon as you go to a more sophisticated test, like the one I mentioned, troponins in the blood increase for myocardial infarction, we already know, because the inventor of this test must have documented how sensitive the test is, how specific the test is. So for that, we have pretty exact numbers. And at the end, what confirms the diagnosis are this kind of more specific characteristic tests. So I believe that will not be a problem. But see, yeah.
I have a question about the model, the mini-max model.
Yeah.
One question that I have is, does the model take into account disease prevalence when it makes the diagnosis? The other question is, could you just say a little bit more about the mini-max and what actually it does?
The problem is I wanted an extra hour to explain how the program works, the technical aspect, and unfortunately it's the first time I'm coming. I understand I couldn't get more than 1 hour, you know. So this is a talk in itself. But I will leave to Thomas to explain that. But let me tell something about prevalence. That is in our 2 books, and that is a very, very good question. Prevalence is very important from an epidemiological point of view. If you want to fight AIDS in Africa, you have to know how many patients. Prevalence, for those who are not doctors, means how frequent a disease happened in a population, you know. So then you need to know how many cases you have in Africa, so you can allocate the proper resources for that. But for diagnostic purposes, it's not only not useful, I consider it could be harmful. Because if the patient has a disease that happens only in 1 million of cases, And then the Bayes formula and all these programs that use prevalence will push down so much the probability of the diagnosis that there is a risk that this diagnosis will be ruled out, you know. And for the patient, it's not 1 in a million. For the patient, it's 100% the disease, you know. So we purposely, and that is described in a whole segment, we disregard prevalence. And that has a fringe benefit that I didn't see at the first moment. But from the Bayes formula, prevalence, it's called prior probability, right? It takes off, by disregarding prevalence, you assign to each diagnosis the same probability, be it rare or be it not rare. And I think that is fair because that gives a chance to the diagnosis to prove its existence by itself, by proper symptoms, you know. And then you can simplify the Bayes formula if all the prior probabilities in the formula, nominator and denominator, are equal. You simply eliminate that. And that creates a new equation that we call positive predictive value, which is novel, the way we determine it. And that the greater the positive predictive value is, the more it will raise the probability of the diagnosis. You want to say something, Thomas? Talk to the microphone about the minimax. He's the creator, by the way, of the minimax. This is his credit. That's why.
So suppose the patient had only one data present and one data absent. In that case, we just apply Bayes formula and that's it, without the a priori probabilities. That is, you assume the data present and data absent are independent. There's no problem with that. And the probabilities will add up to 1. But when there are more data present or more data absent, we create a table where you maximize in the x-axis, in the y-axis of data present and minimize in the y-axis of data absent the probability given the Bayes formula for just one pair. So if you look at the various tables for various diseases, the corresponding entries will add up to 1 over the various tables because it will be just one present and one absent. But when you do minimize in this direction and maximize then in this direction, the final results may add up to more than 1. So that will allow the patient to have more than one disease because different pairs will lend to various results. So what we're measuring is the probability, the data, the disease, as how much does the data present favor the disease, given that there is a lot of data absent that are disfavoring the disease. So the maximum of data present of the minimum of data absent, or the Bayes formula without a pair probabilities for a particular pair. That is all the formula is.
I would like to add that each table, each minimax table represents one diagnosis. And there is a relative independence between tables, relative. So more than one table can reach 100% confirmation, right? That allows diagnosis of concurrent diseases. Okay? Yeah, please.
So my question is, doctors have obviously been around for a while, physicians. And physicians have been around for a while, computer science as well. Let's have a little bit of history now. It seems to me that there's a problem of motivation or trust. I mean, I know for Isabel, the program was developed by a physician whose daughter actually died. If that is the motivation that takes medical science to start moving into this, it may take another 100 years. I mean, it seems to me that the preferred method of publishing their knowledge is medical journals, not actual software or programs like this. So, what is the incentive, this larger problem of, bringing these kind of tools closer to the practicing physicians?
Let me see how can I answer that. You spoke about motivation, motivation is if you have a vision of the benefit that the program will have in the future. And for several reasons, I ask myself many times the same question: why in 5 decades I trying to create a workable system that really diagnoses in real patients, that why was that not created so far? No? Many attempts were done, many errors were committed. In our first book, which is a little more boring to read because it's more theoretical, we had not prototype at that point, it lists all the reasons I see why previous programs did not work, because they considered prevalence, as this gentleman said, and some other errors, you know. And then perhaps to create a program like this, it takes, I have an obsessive compulsive trait, not a real disorder, you know, but I have this obsession since I graduated from medicine, and I worked a lot on that, and even had to make a living practicing medicine, but in the back of my mind, each time I had a complicated case, I said, how would the computer solve that? And after more than half a century, something clicked in my head, and then I had the really very talented mind of my son that helped me then with the logic and with the mathematical part. Perhaps it's a coincidence of factors only. There was a very intense research in journal medicines published, you know, and then this enthusiasm decayed. Perhaps because they didn't reach a good result. Perhaps they were distracted researchers by more gratifying programs like billing programs or so, and that was called the winter of medical diagnostic computation. And what we are trying to create here is a new spring. I don't know if that answered, yeah? Any other question? Okay. Then thank you very much again for your attention.